So we start here. I didn't finish the lecture last time in the sense the one that I started that day. So we'll finish that and start the next topic today as well. This is just to show the Navier-Stokes equation in contract form, because why you need to see it in matrix form is that it is good. So when you write the Navier-Stokes equation in matrix form, you know how to solve it mathematically later on. So what you do is, now you use MATLAB. So in MATLAB also you write, you know how to convert matrices into solutions of equations. Yes. So that's the same thing that you do in CFD. So that's why we want to write it in a matrix form. Then RANS is a Reynolds average Navier-Stokes equation. How we simplify Reynolds average Navier-Stokes equations is now. So in the Navier-Stokes equations, you have the conservative variables, which are here, and the equation of state, stress, and heat flux. So these are the elements of the equation. So what you want to do when you're solving it, you need to have approximations for all of those. When you use simplifications, you can use the thin layer Navier-Stokes equation. So here, if you say it is, when you say it's thin layer, now suppose you have your boundary layer, your whole boundary here and your fluid here, and if you assume a thin layer, that means you are neglecting the boundary layer basically. Then parabolized Navier-Stokes equations means you remove the unsteady terms in the equation, and then if you say Euler equations or inviscid equations, you neglect the viscous terms. You neglect that. So whatever is incorporated with mu, you neglect it. So these are simplifications that you do to the Navier-Stokes, Reynolds average Navier-Stokes equation. And then the next bit is turbulence modeling. So where you get turbulence is, now that's your Navier-Stokes equation, and U can be written as U bar plus U prime. U prime is the random fluctuation of the velocity. So that's what you used for turbulence basically. So in turbulence modeling, now because of the U prime term, you will have more terms in the Navier-Stokes equation, at least 6. Yes. So for those you need to have an approximation, because you have more variables than equations. Therefore, if you don't have enough equations, what you have to do is to make an approximation and write an equation yourself, approximate equation. So that's how you solve a set of equations. So now, if you have two variables, x plus y, you need x and y, you need to have two equations to solve it properly. Yes. X plus y equals 10 and x minus y is equal to 5. So you know the value for x and y both. Yes. So likewise. Then turbulence can be visualized as eddies. Eddies means because of viscosity. So how do eddies form? Now suppose you have a surface like that, and because of the surface you have viscosity, surface friction, and if it is a viscous flow, when a flow tries to flow over this surface, what happens is due to viscosity, you can if you get a streamline, that streamline will curl like that. Okay. So those are the ones that form eddies. And if you have two layers, when one layer tries to slip over the next layer, what happens is it doesn't go straight; it curls. So that is how eddies are normally formed. So if you think about the waves in on water, when you have wind, what happens is you have the surface of water like that, the wind flows over it, and the wind carries the water to a certain extent due to the friction, due to viscosity, and it carries as much as it can hold the water until it drops due to gravity. So that's what happens. So it carries it like that a little bit, and the weight of the water, because of the density, that exceeds the force the carrying force of the wind, and then it drops again. So that's how waves are formed normally. So that the same phenomenon happens in any liquid inside when you have different differential viscous forces. So that's how eddies are basically formed. And because eddies are formed, now the kinetic energy given to the liquid or the kinetic energy given to the fluid dissipates because of the eddies. Okay, so because of the kinetic, so because of viscosity, the energy dissipates. So how you know the energy is dissipated is that when energy dissipates, kinetic energy transforms into heat energy. So the water heats up, or the liquid heats up, or the fluid heats up. So one phenomenon or one practical thing is the water temperature near the seashore is higher than in the deep sea, partly because of the breaking of the waves. When waves break and dissipate energy, the kinetic energy is absorbed by the water. So length scale means, so now these eddies can be small eddies, large eddies, medium-sized eddies, and large eddies. So when you try to mesh, you need to the mesh or the smallest cell should accompany the smallest eddies. otherwise eddy size will be otherwise it will not represent the fluid itself. So now you have what is called large eddy simulation, LES, and you have very large eddy simulation. Meaning, so if you were to model atmospheric flows, etc., so you use what is called very large eddy simulation, VLES. And there is another thing called cascading. Energy cascading means so the large eddies are formed in the liquid or the fluid, then those eddies break into smaller eddies. So when they break into smaller eddies, energy is dissipated, and it breaks further into much smaller eddies, and it goes to the smallest size of eddies. Now with this eddy breakup, this is called the eddy breakup process. In this process, energy is dissipated. The turbulent energy is dissipated. When eddies convect means these eddies carry energy. That means turbulence can generate as well when the eddies carry energy with them. And Reynolds averaging means, now if you write your U or V or P or rho with the turbulent component in it, so that is your U bar, meaning that is the average velocity, and the U double prime, that's the turbulent component. Okay. And when you have when you write the equations in this form, you will have a component in the equation, a multiplication of double prime, and so this velocity multiplication of double prime is called Reynolds stress, and when it comes to enthalpy, it is the Reynolds heat flux. So this is the turbulent component of the equation. Now what you need to solve the equations is an approximation for these Reynolds stresses. So that approximation is called the turbulence model, basically. Okay, so you make an approximation for that one, because you don't have enough equations. You make an approximation. So these approximations are basically turbulence models. So that's it. So this is called the Bossiness approximation. For the mu or the viscosity component, you have a laminar component and a turbulent component. So that one is this component should change. Yes. So you use your turbulence model to compute mu t. You use that one to compute mu t. So the turbulence models can be algebraic, which are called so you have an algebraic equation for mu t, or you can have one equation models, so that's like a partial differential equation or a bold. So there are different approximations like Baldwin-Bath model, Spellat-Almaraz model, etc. And then you have two equation models. So two equation models are like So what is meant by two equation model is now that is your volt, that is your free stream flow. So you have a different equation for the volt, near volt, and different equation for the bulk fluid. So that's a two equation model. So it may have two equations depending on where it is. So that is why we call it a two equation model. So remember SSD or K omega turbulence models are two equation models. So that it treats the bulk fluid separately and the boundary layer separately. So this is an example of an algebraic model.
In what situation do we use these ones?
Okay.
If you want to use SST, what situation do you use it?
That's a good question. If your boundary layer, if you know your boundary layer is important in the flow. So for example, if you are going to resolve the boundary layer for so if it is an aerofoil, for example. Well, in an aerofoil, boundary layer is very important to calculate the drag and lift. So you need to resolve the boundary layer. Therefore, you have to use a higher order turbulence model, like SST, at least K omega or SST. K epsilon doesn't work. Well, it works, but it won't give you a good answer, accurate enough answer. But on the other hand, you are trying to resolve a flow problem inside a tube, just a large tube. Okay? Then you can consider the boundary layer to be fairly thin, and you are resolving the bulk fluid. In that case, K epsilon model would be good enough. Okay. And if you just want to know the flow field, etc., if you are not that worried about the boundary layer treatment, you can use one. And the when you go higher when you use a higher order turbulence model like SST or K omega, your computational time will increase because you have to solve more equations. That means the numerical demand on the computer is higher. So the time taken for your solution is longer. So if you don't want to waste that time, or if you think that is a waste of time, you can use a simpler model and get an answer quickly. But if you're not worried about the boundary layer, that answer may be as good as anything. Even if you use the SST model and the K epsilon model, you might get the same answer, very similar answers. It depends.
To try each method then.
Yeah. So normally when you start when you are starting a problem, what you do is you start with a simpler model and get an answer for the flow field first. And then, so with that you know that your CFD model works. Okay. Then you change, then you refine it by changing the turbulence model, etc.
So it's like a conversion study.
In a sense, yes. Yeah. So I told you this because now if you have a turbulent reacting flow, you don't start with combustion at the first instance. So you get a domain done, and then you have an isothermal flow inside it and see whether the flow field works. And then only you introduce the complexities into the flow. So using a turbulence model is also similar. So you can use it. Okay, and the good thing about K epsilon and k omega also, those models are pretty good, giving you decent results, and they don't crash very quickly either. And therefore, if you are doing it for the first time, just use k. If you are considering turbulence, use the k epsilon model and get an answer, and then see what the other models will give you. That's why you need to have an understanding of the physics before you use CFD. So CFD doesn't it's not a black box that gives you a.
When you say considering turbulence, you mean like normal airflow? Like just normal airflow would be turbulence? No?
No, you need to calculate the Reynolds number of your fluids.
Yeah.
So if your with the Reynolds number, if it is air, if your fluid is air, if it is less than, if it is like 200,000, it's not
So would
turbulent.
you say that it's static then?
No, it's not static. You can just use. You don't have to use a turbulent one.
Okay.
Just say laminar flow. So the limit is 500,000 for air Reynolds number. Beyond 500,000 it will be turbulent. For pipe flow, it will be 2,500. So there are different models for Smith model, Baldwin-Lomax model, and PDT model. So these models improve step by step. So, but still they are algebraic models. And then you have one equation models. So when boundary layers separate, you can use Spalart-Almarat model. So it is good for especially 2D applications and for where turbulence is not that prominent. Then you have two equation models, for example, K epsilon model, K omega model, and SSD model. SSD model is also a two equation model, but it uses the K and epsilon differently to K omega, K epsilon model. Yeah, so that's where we stop the discussion of this turbulence models. And do you have any further questions before I move to the next lesson?
Realistically, it's experience that says what's good and what's not on your results.
Say that again, sorry?
What's good and what's not on your results when you get this purely down to experience.
Yeah, so a CFD engineer or a modeler should have experience doing a lot of examples first. Yeah, so that and you analyze your flow and see what is going on there, why, whether it resolves the boundary layer, whether it doesn't resolve the boundary layer, whether it resolves the bulk flow correctly, whether it resolves the combustion or reaction correctly, and so on.